Last time we were discussing optical absorption in semiconductors and the different types of transitions involved. As shown in this diagram, we were discussing the fundamental absorption at the band edge, which rises very sharply at energies more than about 1 electron volts. In particular, last time we discussed what is the difference between direct and indirect bandgap semiconductors, and we showed that for the case of direct gap semiconductors like gallium arsenide, the absorption rose very sharply at the absorption edge, and the absorption coefficient was proportional to h nu minus e to the power half, whereas in the case of indirect bandgap semiconductor like silicon, the absorption coefficient was proportional to h nu minus eg minus ep to the power 2. Now, in this case, of course, we had two cases of phonon emission as well as phonon absorption. Let us go back to looking at various other types of fundamental absorption which may occur when the transition probability is forbidden. And thereafter in this lecture we will talk about other types of electronic transition mechanisms, such as impurity absorption and absorption due to free carriers. Now, in the case of forbidden direct transitions, we may have a case that at k equal to 0, transitions are forbidden according to quantum mechanical selection rules, but at k not equal to 0, we have transitions allowed. That means transitions are allowed at k not equal to 0. In this case, the probability of transition from the initial to the final states is found to be proportional to h nu minus eg. Whereas in the previous cases, we had assumed that this probability of transition was independent of energy. Now we know that for the density of states function for direct transitions is proportional to h nu minus eg to the power half, as we had derived previously. Now, if the probability is proportional to h nu minus eg, then the overall absorption coefficient goes as the product of these, and it goes as, say, some a dashed to the power h nu minus eg to the power 3 by 2. So this is a special case when transitions are forbidden at k equal to 0, but allowed at k not equal to 0, when alpha goes as h nu minus eg to the power 3 by 2. Now, let us take some special cases. Another important case is when a semiconductor is heavily doped. This is important because, as you know, when you want to make devices like PN junction LEDs or PN junction lasers, one of the regions is usually fairly heavily doped. It's either a P plus N or an N plus P junction. So heavy doping effects in semiconductors are important from the study of optical properties. Let us take some of the consequences of heavy doping. One of the results is what is known as the Moss-Bernstein shift. Of the band edge, in which the band gap, effective band gap measured, is seen to increase over the actual band gap, which is the difference between the conduction and the valence band, by a value, say xi n, which is a function of doping. This can be understood quite easily from the diagram showing the density of states against energy. For the conduction band, we have parabolic band starting at EC. For the valence band, we have a density of states starting from EV. And now, in the case of heavy doping, the Fermi level is no longer in the band gap, but the Fermi level is somewhere above the band gap. This is when the material is degenerate and electrons occupy all levels up to a value xi n. As a result, when light is incident on the semiconductor, we have absorption possible between electrons occupying the valence band and empty levels, which are no longer at EC, but empty levels are placed at an energy xi n above EC. So what we measure is obviously EC plus xi n, and this effective increase in band gap as measured through optical absorption is called the Moss-Bernstein shift. And as you can see, the shift will be proportional to the doping. It will increase with doping. Let us look into this in a little more detail. If we can again draw the energy band diagram, E against K this time. The energy in the conduction band is given by h squared k squared over twice mn star. In the valence band, the whole energies are given by minus h squared k squared over twice mp star. and if the Fermi level is in the conduction band at an energy above EC, then what happens in the case when the temperature is no longer zero, the temperature is something finite? The Fermi level could be here, and the distribution of electrons in the Fermi level, in the conduction band, is given by a distribution function, the Fermi direct distribution function. And this energy is then psi n minus 4 kT. This is the Fermi function as a function of energy. So in this case, we have the C band filled up to h squared k squared by twice mn star, which is equal to psi n minus 4 kt. Now, since we know that n into p is always ni squared, there will be a concentration of holes in the valence band, and so due to momentum conservation, the energy at which optical absorption will start is given by h nu is equal to Eg plus h squared k squared over twice m into 1 by mp star plus 1 by mn star. And so we see that the edge is effectively increased due to the occupation of electrons in the conduction band and the occupation of holes in the valence band. And as drawn, we find the conduction band contribution is much larger because the effective mass, Mn star, is much smaller. If this is much smaller, this term is much larger than this term. So the effective measured band gap is no longer the difference between EC and EV, but it's increased by this factor. Now, one can actually look at the results in a material like indium antimonide, which is a semiconductor with a band gap of 0.17 eV at 300 degrees K. And how does the optical band gap as measured through optical absorption vary with doping? Since the band gap is quite small, the intrinsic carrier concentration is quite large, of the order 10 to the power 17, and we find that if n is increased, then the band gap starts off at 0.17 eV, and beyond 10 to the power 18, it rises quite sharply, and it can rise to almost a value of about 0.45 eV with doping of the order of 5 × 10⁻18. So this is quite important because historically, because when indium antimonide was first prepared, the impurity level was rather high, and the first optical absorption measurements gave a band gap values around 0.4, 0.3. But it was only after indium antimonide was purified by zone refining and very pure material was prepared that one found that the band gap actually is 0.17. So if a material is impure, it has a lot of donors, especially, then the effective band gap measured optically is much larger than the actual band gap. So this is important because, as you know, optical measurements are very important in determining the band gap of semiconductors. This is one way of determining the band gap of semiconductors, and we know that, for example, for silicon, e.g. optical is 1.14 eV. For germanium, another indirect band gap semiconductor, this is 0.67 eV at 300 K. For gallium arsenide, it is 1.41 eV. For indium phosphide, it's 1.34 eV. So when we have relatively pure material with no Moss-Bernstein shift, we can get directly the value of the band gap, the difference between EC and EV, as well as the nature of the band gap, whether it's indirect or direct, from optical absorption measurements. Right. Let's go on to the other effects that occur when we have heavy doping. I will just discuss. We have already seen the Moss-Bernstein shift, which is due to heavy doping. There is also an accompanying effect called band gap shrinkage. Now, what is this band gap shrinkage? Band gap shrinkage means that at heavy doping, EG effective is not just EG plus xi n, which is due to the Moss-Bernstein shift, but there is a decrease delta E0, which is found in both direct and indirect band gap semiconductors, and this is also called band gap narrowing. What is this due to? Delta E0 can be divided into two components. One is band gap narrowing due to electron donor type of interactions, and there is another component due to electron interactions. This band gap narrowing can be quite large. It can be of the order of 0.1 or 0.2 electron volts, and together with the Moss-Bernstein shift, it can give rise to quite remarkable effects. For example, we know that indium phosphide has a band gap of 1.34 eV at 300 K. But if we dope it at 2 × 10⁻20 per centimeter cubed, what was found is that the effective optical band gap became as large as 2 electron volts. Now, 2 electron volts corresponds to 1.24 by lambda, and lambda is then 0.62 eV. So, strong red emission was observed from indium phosphide. 0.62 microns. Right. Thank you. So, although the band gap of indium phosphide is 1.34 eV, one found that with heavy doping, the edge shifted to much shorter wavelengths and giving rise to red emission. If one is to go into a little more detail about band gap shrinkage, delta E is equal to delta E electron electron plus delta E electron impurity, and it can be shown that the electron interaction is given by an expression depending upon the refractive index, and it essentially goes as n to the power 1/3. Now, if n is the total number of carriers in the semiconductor, n to the power 1/3 obviously means that n to the power 1/3 is proportional to the average electron-electron distance, the average separation between electrons. Whereas if we look at electron impurity interaction, this is the Nd minus Na is the effective positively charged impurity concentration divided by epsilon 0 epsilon r q squared, where q squared and Qp is the reciprocal of the electron screening length. The question was, what is the meaning of electron screening length? One can explain this interaction by looking at a diagram. Suppose you have electrons in the conduction band and you have certain donors and maybe a few acceptors. So the effective charge is the effective positive charge is Nd minus Na, and one can say that if there is an effective positive charge, then the potential around the positive charge is somewhat like this as a function of distance, and obviously this positive charge attracts electrons in its neighborhood, so it is the length beyond which the effect of this positive charge is not felt. So the positive charge, the donors, are screened by the electrons, by the conduction band electrons, and so 1 by q is the reciprocal of the screening length. It is the length beyond which the electrons in the conduction band do not feel the effect of the positive donors. Now, the screening lengths can be calculated, and for the case of degenerate and non-degenerate bands, for non-degenerate bands, EF below EC, QP squared is E squared by epsilon 0 epsilon r kt by into NP, where NP is the concentration of electrons. So as NP increases, QP also increases, and the reciprocal of the screening length then decreases. For the degenerate system, which we are more interested in, when EF is greater than EC, then we have QP squared is equal to 4 pi E squared epsilon 0 epsilon r 8 squared 3 pi pi to the power 1/3 MP NP to the power 1/3. So this is approximate distance between screening electrons, and in this way one can actually calculate what is the screening length, and thereby what are the two components of band gap shrinkage due to electron-electron and electron impurity interactions. To show you some experimental results, this is photoluminescence results. Photoluminescence is the reverse of optical absorption, that is light emission due to transition from the conduction band into the valence band. And if you just look at this, this is a function of wavelength versus intensity. The thing to note here is that this is indium phosphide, so the band edge is near 900 nanometers. But if you have relatively light doping, 1.2 10 to the power 18, the photoluminescence edge is at 1.41. Slightly heavier doping, 6 10 to the power 18, 1.44. 1 10 to the power 19, the edge is shifted to 1.48. And this is all at 77K. If we go in for still heavier doping, 3.46 10 to the power 19, this edge is shifted to near 775. And at 5.5 10 to the power 19, this is shifted to 1.66. So this peak is a much shorter energy than the band gap, which is near 900 nanometers. These are results obtained for indium phosphide doped with selenium, and if you just see these results, this table sums up all the results obtained in our laboratory, that if you have a doping of about 10 to the power 18, then the edge is near 1.31 as expected. And if the doping goes up to 10 to the power 20, the edge shifts to 1.91. So there's a considerable shift in the photoluminescence edge or the optical edge, and it is not just the Moss-Bernstein shift. The Moss-Bernstein shift, if you did not take the band gap shrinkage into account, this value calculated would be something like 2.1 or 2.2. So there's an increase due to the Moss-Bernstein shift, and there's a decrease due to band gap shrinkage. So these points are very important when it comes to studying the optical properties of lasers and similar materials. The question is, which of the two terms dominates, Moss-Bernstein shift or the band gap shrinkage? Well, from the results you see the band gap is increasing, right? So obviously Moss-Bernstein shift dominates over band gap shrinkage. Okay. In this particular case, especially because for indium phosphide the effective mass is very small. Notice that the Moss-Bernstein shift had a term 1 by Mn star. So since 1 by Mn star is quite small, Moss-Bernstein factor dominates over the band gap shrinkage. But that's a good question. In some cases, in the case of silicon, where the effective mass is very large, relatively large, then the effective band gap decreases. For example, in devices, when you have silicon devices, if you have heavily doped devices, then if you study the electrical characteristics, you will find that P into N is Ni squared, but if you look at the same band gap shrinkage through electrical properties of, say, junctions, you will find that N into P in thermal equilibrium must be equal to Ni squared, but it is Ni effective squared. And since this is larger than Ni squared, because Eg effective is less than Eg at low doping. So as a result, this NP product is larger than that you would expect if the material was not heavily doped. This is important in silicon transistors, NPN devices, etc. It is found that as the edge shifts for an indirect bandgap semiconductor, where normally phonon scattering is involved. As we have seen, optical absorption involves phonons. But for heavy doping, you can get momentum conservation from either impurity scattering or electron-electron scattering. So phonons need not be involved. And as a result, one finds that alpha h nu is now proportional to n, where n is the number of scattering centers into the usual expression h nu minus Eg minus xi n squared for indirect bandgap semiconductors. So we have alpha to the power half h nu is proportional to n to the power half. And if we take the derivative, d root alpha over d h nu is proportional to n to the power half. And this is what is found experimentally. We plot the slope, we plot alpha to the power half against this, and we take the slope, and the slope, this is as a function of h nu, and the slope is found equal to half. So not only does the band edge shift, but the nature of scattering also changes. It is no longer phonon scattering. You can have impurity or electron-electron scattering. Now, for direct gap semiconductors, it was found as we've seen earlier, Eg effective is equal to Eg plus xi n minus delta E0. This is the mass burst time term, and this is the bandgap shrinkage term. There is a third effect of heavy doping, which I'll go into very briefly. This is band tailing. This means that under heavy doping conditions, say we have heavy n-type doping with donors, the nature of the density of states functions itself changes, and we no longer have just a parabolic distribution, but we have a gradual decrease in the density of states, tapering down into the band gap, which is called band tailing. And this distribution can often be approximated by a sort of exponential decrease of the density of states. Whereas for lightly doped semiconductor, the density of states would just go like that. Here, for heavily doped materials, we have a band tailing effect. This has also been examined experimentally, and it is found that for gallium arsenide, for a lightly doped material, the the edge would be somewhat like that at 1.41 eV, but this is obviously proportional to h nu minus Eg to the power half for ideal direct gap semiconductor. However, experimentally it's found that for doping concentration of the order of 10 to the power 18, you have an exponential absorption tail due to band tailing, and we find that the edge is extended into the lower band gap region. In order to explain this, one can draw a diagram like that. This is the band tailing in the conduction band. We neglect the band tailing in the valence band for the moment, but there are holes in the valence band, and the whole Fermi level is moves into the valence band, and one can take this as an exercise. One can show that in this case we have the n initial states is proportional to EV to the power half. We're trying to, if you want to try and calculate absorption in this case with band tailing, then we're considering excitations like this from the valence band into the conduction band. The initial electrons are in the valence band where the density of states is EV to the power half. The final states here in the conduction band we can assume varies exponentially due to band tailing E by E0, and as before, if we assume that PIF is independent of energy, then you can take it as an exercise. You can show that alpha h nu is some constant EV to the power half exponential E by E0 dE, where the limits of integration are xi p and h nu minus xi p, where xi p is the Fermi level in the valence band. And if we calculate d log alpha d h nu, the slope, it can be shown that the inverse of the slope is equal to E0. So this E0 is an experimental parameter which is related to the inverse of the slope of the optical absorption edge. And this tailing is known as an Urbach tail, exponential Urbach tail in the optical absorption edge, which is seen in many semiconductors when you have heavy doping effects. The next topic, which I will just enter into the preliminary fashion, is excitonic absorption. We find that when we approach the absorption edge, then there's some, when the wavelength is decreasing and we are approaching the fundamental absorption edge, there are small discrete peaks, transitions due to excitons. And this gives rise to peaks in the case of direct gap materials and steps in the case of indirect gap materials. What are excitons? A simple picture of weak excitons comprises of an electron and a whole pair which is bound due to Coulombic attraction. And so it takes a little energy to dissociate the bound exciton, and one can say this is not it's a two-particle excitation. So one can say if this is the conduction band edge, the energies of the excitons are slightly below the conduction band edge, and so a certain amount of energy is required to free the excitons, break up the bound electron hole pairs. If you think of this along the lines of a hydrogenic impurity, then you can say that the excitonic binding energy is Mr Q4 over exactly the same as in the case of the hydrogenic model, which we also apply for impurities, hydrogenic impurities in a semiconductor, where L are integers, 1, 2, 3, etc. And if we simplify this, then this is nothing other than 13.6, the usual hydrogenic expression, over L squared, Mr star over M0, 1 by epsilon. Epsilon r is the relative dielectric constant, and this is exactly like impurity absorption in a semiconductor, except that Mr star is the reduced effective mass. We have a bound electron hole pair, so 1 by Mr star is 1 by, say, Me star over 1 by Mh star. So the total kinetic energy, total energy of the exciton is the sum of the kinetic energy, which is H squared K exciton squared over twice Me star plus Mh star minus the binding energy of the exciton. And as I'll show experimentally, what does this give rise to? That we have very pure semiconductor at low temperature. Take the case of gallium arsenide at 294K, one has a characteristic absorption edge without any special features. As we know that the band gap increases as we go down in temperature, at 78K we have a little structure like this. And if you go down still further in temperature at 21K, we have a shift in the absorption edge due to increasing band gap, and these features, this peak, is due to the creation of excitons. Notice that the sharpness of the peak decreases, the line width decreases as you go down in temperature, and the peak intensity also increases as you go down in temperature. So the observation of excitonic lines is an indication of the purity of a semiconductor, and it occurs when you have extremely high purity semiconductors. What happens in the case of indirect gap material like germanium? Then one has small steps. This is at 0.77 eV near the indirect gap, and as you know, germanium has a direct gap also. Near the direct gap you get the typical peak at about 0.89 eV. So this is the optical absorption spectrum of germanium at low temperature at 24K. Corresponding to the indirect gap, one gets a step, and corresponding to the direct gap, one gets a peak due to excitonic absorption. Remember, the band structure of germanium can be shown as follows. To explain this result, so corresponding to the indirect gap is about 0.77 eV, and there is a direct gap here at about 0.89 eV. So there are excitonic absorptions associated with both the indirect and direct gaps.